Okay, today we are looking at the Unit 4 Lesson 9 video. We're in Chapter 12 out of the textbook, and we're going to be talking about inverse trigonometric functions. We're going to start off with a key concept on basically what the inverse trig functions look like, what their domain and range are, and a model of one of them. So we're going to start off with arc sine or inverse sine. These two things mean the same thing. You can see here they have arc sine of x and sine inverse of x. These mean the same thing. Some textbooks use one term and some textbooks use the other. Some calculators use one term and some calculators use the other, but they mean the exact same thing. It's the same for cosine and for tangent. There's two different ways of saying the same thing. Basically, because these are inverse functions, just like we studied inverse functions earlier in the year, when you have an inverse function, you basically have flipped the x and the y values of the function. So while the sine of x and the cosine of x have a range between -1 and 1, the arc sine or the inverse sine and the inverse cosine have the domain between -1 and 1. Conceptually, the inverse trig functions for sine and cosine take the regular sine wave and the regular cosine wave, and rather than moving them up and down across the x-axis, they get flipped so they move back and forth up and down the y-axis. And that's essentially what the inverse does. The inverse tangent function does the same type of thing. While the inverse tangent function, I'm going to trace it with my mouse, looks generally like this and cuts through and comes up, the arc tangent or the inverse tangent would look like this or this, depending on the sign of your tangent function. So that's the basic concept. Let's get into an example. Our first example is asking us to evaluate an inverse trig function. And it says we need to find the value of the inverse sine of square root of 2 over 2, and we need to write the angle measurement in both degrees and in radians. So there's a couple ways of doing this. Basically what you want to do is think about the unit circle and find an angle on there that has a sine value or a y value for the coordinate point of square root of 2 over 2. And there's a couple angles that you're going to be able to find that have square root of 2 over 2 as the sine value. And they would be pi over 4 and 7 pi over 4 or negative pi over 4. So here we go, method 1, use unit circle. Pi over 4 is our first one. We have a y value of root 2 over 2. So that's one angle. That's 45 degrees or pi over 4. So that's one of your answers. You can also use a calculator. And the way you would press that on the calculator is you'd press second sign, which gives us the inverse function, and then the square root symbol, to close your parentheses, divide by 2, hit enter. It will tell you 45 if you're in degrees, and it'll tell you you need to be in degrees here for this. And then manually you have to convert the 45 degrees over to radians, which would be pi over 4. Part B, we're going to find the value of arc sine of -1, and we're going to write the angle measurement in both degrees and radians. So looking on the unit circle between -90 and +90 degrees. You could do this on the calculator also, but I like the unit circle personally. Looking in between those values, the angle that has a sine of -1 would be the 3 pi over 2 angle or the negative pi over 2 angle, which is the 270 degree angle or -90 degree angle. Because we're keeping in this interval between -90 and +90, you want to go with -90, which is the same as negative pi over 2. So our answer is -90 degrees or negative pi over 2. And again, I know this is kind of difficult right now just because I don't have the unit circle pulled up every single time we talk about one of these examples. But if you're doing this lesson at home, you want to make sure that you have a copy of the unit circle next to you while we're talking about all the problems in this section. And if you're in class, then obviously you know where the unit circle poster is in my classroom. Here's a check your progress problem for example 1. Go ahead and pause the video while you work through it. When you have your answer, go on to the next slide. Okay, our answer this time is D. The inverse cosine of root 2 over 2 is 45 degrees, which is also pi over 4. Part B, here's another problem. Go ahead and pause the video while you work out your answer. And when you have your answer, go on to the next slide. And our answer this time is C, 180 degrees, or just pi, for the inverse cosine of negative 1. For example 2, this is finding a generic trigonometric value that is not on the unit circle. We need to find the value of the tangent of the inverse cosine of 4 over 7. And we're going to round our answer to the nearest hundredth. So you can do this on the calculator, and not you can, you have to, because 4 over 7 is not any of the coordinate points from the angles on the unit circle. So if you ever are given a problem like this where you notice that this fraction in here, or the number, if it's not a fraction, is not one of the coordinate points on the unit circle, you're going to have to use your calculator because there's no other way to do it. So to do this on your calculator, you would press tangent, and then cosine, second cosine to get the inverse function. 4 divided by 7, close your parentheses, close your second parentheses, hit enter, and you get 1.436. We're going to round to the nearest hundredth, so that's 2 decimal places, which is going to make our final answer 1.44. Okay, here's the one to check your progress on. Same process here. Go ahead, pause the video, get your answer, check it out on your calculator, and then when you have it, we'll go on to the next slide. Okay, our answer for this one is choice B. It's 1.12 radians. For example 3, we're looking at a problem that could show up on the SAT. And it says if the cosine of theta is negative 0.86, find theta. So we have 4 options. What we're going to need to do for this is to get theta by itself. And so we know that to move cosine to the other side of the equation, we're going to have to do the inverse function. So that's inverse cosine or arc cosine of negative 0.86. And when you type that in your calculator, let's see what we get. It appears that we would get a 149.3, and that answer, of course, would be in degrees. You could also convert that. You could do this in radians if they asked you, but obviously our answer choices were in degrees. So we are going with, let's see if they have the answer choices up here again. They didn't pull them up again, but this number, 149.3, that was choice D. So this is pretty simple. It just involves using the calculator. You've got to make sure you have the TI calculator with you to be able to do this stuff. Here's one for you to check your progress on. Go ahead and pause the video while you type this in your calculator. When you have your answer, go on to the next screen. Okay, our answer this time is B, negative 45 degrees. And we can move on to example 4. Example 4 is a real-world problem on water skiing. It says a water ski ramp is 5.5 feet tall and 12 feet long, as shown below. Write an inverse trig function that can be used to find theta, then find the measure of theta, round to the nearest tenth. So we've done this again already in this unit. When you look at this angle and you look at these sides, you should know that the 5.5 is the opposite side and the 12 is the hypotenuse. When you have opposite and hypotenuse, that means the sine function. So we're going to need to do the inverse sine of 5.5 over 12, and that will give us the measurement of angle theta. When you type that in your calculator, you will get 27.3 degrees. Therefore, the angle of the ramp is about 27.3 degrees. Okay, we got one problem to check your progress on. Same concept here. Go ahead and pause the video, work out the answer, and we'll see the answer on the next slide. Okay, our answer this time for the inverse sine of 8 over 20 is about 23.6 degrees. Choice B. Okay, that brings us to the end of the Unit 4 Lesson 9 video on inverse trig functions.